In this segment, I want to talk about the spring force. So, first of all, springs can exert a force. You probably knew that. Here's a spring. It's a great big long one. I use it for demonstrating waves sometimes, but it can exert a force. If I pull it over here, then I can just feel that force exerted on my hand. And if I let go, it flies back. Okay, great. So, definitely springs can exert a force, right? So, what could we figure out about that force that the spring exerts? Well, if I apply a force on the spring in that direction, then the spring exerts a force in that direction, right? It just makes sense, right? So if I displace the end of the spring in that direction, then the spring pulls in that direction. Great. I have a lovely picture here that shows the thing. In this slide, we see here a relaxed spring, and just like I was just demonstrating, if I pull this spring to the left, then the spring pulls back to the right. So the force of the spring on my hand is to the right if I displace it to the left. Another thing about springs is that if I pull the spring a little bit, then I get a little bit of force. Just a little bit, that's easy. If I pull it a little more, I get a little more force. If I pull it a little more, I get a little more force, and this is actually starting to get kind of hard to hang on to with my little fingers. So at this point, I'm actually experiencing quite a large force from the spring because I've stretched it quite a bit. If I stretch it less, I get less force on my hand. Even less force. Okay, so the amount of force that a spring applies depends on how much it is stretched. In fact, it's proportional to how much it's stretched. So if we were to make a plot right here of force versus how much I've stretched it, so delta x here means how much is the spring stretched. We don't care about the original length of the spring. We only care how much it is stretched. So here we see force versus how much it's stretched. We see that all of the points lie right along a plane. So we can say that the magnitude of the spring force is proportional to how much it is stretched. And so this proportionality constant ends up being pretty important. It turns out that this proportionality constant, we call this the spring constant. And the spring constant tells us how stiff a spring is. So now it turns out that we're going to be wanting to use this equation right here. This is the magnitude of the spring force, right? And recall that in our strategies for solving force problems, we draw our object of interest, we draw the forces acting on them, and then we apply Newton's second law. And the way we've done that is when we apply Newton's second law, right, we put in the magnitudes of the forces, and then we decide on plus or minus depending on our coordinate system and the free body diagram, right? And so we're going to use that same strategy here. And so the magnitude of this force is equal to the spring constant times how much the spring has been stretched. Now, let's think about the direction of that force, though. We just talked about the magnitude. Let's think about the direction. Now, it turns out that a spring like this, right, you can see that the coils are all super tight. This is a pretty typical spring. A spring like this can only be stretched. It can't be compressed. But if you see the springs on a big truck or something like that, then they've got space between the coils, as shown here and as shown here. So a spring like this can either be compressed. In this picture, I could push it to the right, or stretched, I could pull it to the left. And so that spring here, if I compress it by pushing it to the right, then the spring force pushes back to the left. In other words, the force of the spring is always opposite to the compression. If I make the spring, right, so if I push on the spring to compress it, if I'm pushing on it to the right, then the spring pushes back to the left. If I pull on the spring to extend it, then delta x is to the left, and the spring force is to the right. So, in this case, the spring force is always opposite in direction to the change in length. So if we think of the change in length as a vector, which we certainly can, then this gives us the magnitude, but since the spring force and the delta x are always opposite, we should include a negative sign in here. Now, this equation is known as Hooke's law. It has a famous name. It is Hooke's law. It turns out that Hooke was a contemporary of Newton. He's not quite as awesome as Newton, so he just gets a little law about springs, apparently. That was his contribution. Okay, anyway. Hooke's law tells us about the directions here. It tells us that, yes, the spring force is proportional to the displacement, to the stretch, I should say, and it is opposite in direction to the stretch. Now, again, I want to be clear, though, this is kind of our big money equation, because usually we look at the forces and we decide on the directions by looking at the situation, right? And we draw those on our free body diagram, and then we look at our coordinate system and the free body diagram and decide whether those forces are positive or negative. And we should continue to use that strategy. I see a lot of times students will let this negative sign throw them off because they'll go through our force problem steps and then throw in that negative sign at the end when they plug in F equals negative kx. And it's just double counting. So if you've already accounted for the direction in your force problem steps, you don't need to account for this negative sign here. Okay, not too bad. Here's a quick clicker question. Which spring has the largest constant? So here we see the force of the spring on the vertical axis, and here we see on the horizontal axis the amount that the spring has stretched. We see three different springs, A, B, C, and three different springs, A, B, and C. And so which of these has the greatest spring constant? Well, recall that the magnitude of the spring force, the magnitude of that, is equal to K times delta X. And I'll just throw some magnitude signs on there just to make sure that we know we're not talking about the direction, because with the direction we would need a negative sign there, right? If we were to graph this, right, remember y equals mx plus b, right? Y equals mx plus b. And so the slope here would be K. Of course, our x's correspond nicely with a y-intercept of 0. Indeed, we do see a y-intercept of 0. The slope is K. The greatest slope is the greatest spring constant. I'm looking at answer A. Okay. I have a couple of quick examples to do. A 20 centimeter long spring is attached to a wall. When pulled horizontally with a force of 100 newtons, the spring stretches to a length of 22 centimeters. What is the value of the spring constant? Okay. So here, let's hook this to a wall. And there's my spring. It said originally it was 20 centimeters. When pulled, though, it stretches to 22 centimeters. So. Okay, so here's my drawing. Our original length is 20 centimeters. My stretch is 2 centimeters. And this pull is 100 meters. Okay, what is the value of the spring constant? Well, let's just treat this like a force problem and see how far we get. If it's just being held there, then the sum of the forces in the x direction equals 0 on what? Well, a lot of times students want to do the object of interest is my spring. Hey, a spring cannot exert a force on itself. So if we're trying to get onto the inside of that, into the K, right, which is part of the spring force, if we're thinking about the spring force, it's got to be something that's not the spring. Gosh, what should it be? You know what? Our little dot right here should be our object of interest. All right. And so what we would have then is we would have the pull here and spring in that direction. Okay, so we know the net force in the x direction is 0. So looking at our free body diagram, that means we have a pull minus a spring force equals 0. I just want to notice something here. Minus k delta x equals 0. So now this is that negative sign that I was talking about right here. This is that negative sign that I was talking about that sometimes trips students up. Right? Notice when I plugged this in, I didn't include the negative sign from Hooke's law. I just include the magnitude because I already decided the direction here, right? When I drew my free body diagram, I decided that the spring force was in the negative direction. That's where this negative came from. When I plugged in for the spring force, I just plugged in the magnitude here. Now, there's ways for accounting for it. If you keep track of every vector, then it all works out. I think this is the way to go. Okay, So now you can see that we can just do some quick algebra, and we end up with K equals the pull over delta X. So that's 100 newtons. Now what's delta X? This is part of why I do this example. It's not 20 centimeters. It's not 22 centimeters. Delta X is always how much the spring was stretched. So that is just 2 centimeters, or 0.02 meters. Okay, so we run our calculator and we get 5,000 newtons per meter. Yeah, that's a pretty big number, isn't it? Is it ridiculous? Well, not really. Remember that a newton is a small amount of force. Recall that a newton is about a quarter pound, right? So newton is not a lot of force, and a meter is a pretty long stretch, right? So this says, whatever the spring is, if I stretch it for a whole meter, then the force it will apply to me is 5,000 newtons. Well, that is a lot. That's over 1,000 pounds. That's a large force, but again, a meter is a long stretch. So this is a pretty stiff spring, but it's not an unreasonable number. Notice the units, right? Newtons per meter, right? And so again, it says, how many newtons does it take to stretch a spring by a meter? That's another way of picturing it. And so this K value, right, it tells you how stiff a spring is. So a real loose, floppy spring, a real loose one, that's going to have a low K, right? A real flimsy one, a spring from a ballpoint pen is going to have a very low value of K. A very stiff spring, something that's very hard to compress or very, very hard to stretch, that's going to have a high K. A spring on a big truck, a big truck spring, would have a very, very large value of K. That's a pretty large value, but totally reasonable. Let's do another example. The same spring is now used in a tug-of-war where two people pull on the ends, each with a force of 100 newtons. How long is the spring while it is being pulled? Okay, so here's my spring, and maybe that's the original length, and that's the stretch, right? So originally it was 20 centimeters. Now we're stretching at delta X. Recall that when we hooked this to the wall and we applied a 100 Newton stretch or 100 Newton force, recall we got 2 centimeters of stretch, right? And that allowed us to figure out that K was 2,000 newtons per meter. How far is it going to stretch this time? Why don't you go ahead and, I don't know, think about it. Pause the video, make a prediction, and then we'll do the math. Okay, I hope that you took the time to make a prediction. Let's do the math, and let's see. Again, I think we're going to want to, what's our object of interest? Where are we going to sum the forces? Well, again, I think we should just sum the forces on this end right here. Again, we can't do it on the spring. If the spring was our object of interest, we'd just get 100 newtons that way, 100 newtons that way. It's not accelerating. True, not interesting, and not helpful. So we don't want to use the spring itself as our object of interest. I think we should use this end right over here where I'm applying the force and where the spring is pulling back. And so define a coordinate system, standard issue coordinate system. Sum of the forces in the x direction equals 0. It's not accelerating. We have 100 newtons minus. This should look familiar. Isn't this the exact same as what we had a minute ago? It's just in that case we solved for K and we knew delta X. In this case we've got K and we're looking for delta X, but same dang thing, right? We're still gonna get 2 centimeters. So is that what you predicted? I think this is a rare prediction in this case. When I do this example in class, most students predict that it will be 4 centimeters, which kind of makes sense. I mean, it's wrong. I guess what I mean by that is I can see why you might think that, because it kind of feels like maybe we've got more pulling because we got people pulling on both sides, but This is 100 newtons going this way on this spring, right? Earlier, in the first problem, we had a wall here, right? So in the first problem, we had a wall here, and that's what was holding the spring. But guess what? The spring wasn't accelerating, which means that if I'm pulling on the spring with 100 newtons in that direction to stretch it, and it's not accelerating, then guess what? Again, think of the spring as our object of interest. If it's not accelerating and there's 100 newtons that way, then there's definitely 100 newtons that way also, right? Because it's got to be in equilibrium. So if it's in equilibrium, and there's 100 newtons there and 100 newtons there, hey, who cares what this 100 newtons is from, right? Right? If I hook the spring to a wall, that wall is exerting a force of 100 newtons on the spring. If instead it's me and I hook my finger there and I'm pulling on it, well, in this particular case, I'm indistinguishable from a wall, right? It was really, as long as the end of the spring isn't moving, it doesn't matter at all if I hook it to a wall or a person, right? This makes us feel like it's going to be different because a person's active, a person's pulling with muscles. It doesn't matter, right? It doesn't matter. The wall does the exact same thing as a person there. It's identical situation to the first. So we get the same stretch.